Okay, we're now going to discuss the idea of regression, starting with linear regression, also known as fitting a straight line to the points. So let's go back to our earlier example of rioting R versus the price of wheat W. So here's the amount of rioting changing over time, and here's in red the price of wheat changing over time. And we can look at that chart and say, oh, it looks as though there's a correlation between them. It looks as though as the price of wheat goes up, the amount of rioting goes up, and as the price of wheat goes down, the amount of rioting goes down. They vary together. And that is something we might expect, as we discussed earlier. And we said that we can examine that in another way by plotting the price of wheat against the amount of rioting at each point. So we'll get a scatter plot of wheat along here and the amount of rioting up there. And again, we can look at this and say, oh, it looks as though, there is a relationship between them, that as the price of wheat goes up, the amount of rioting goes up. And I'm going to define something called the covariance, which is a measure of this tendency of the variables to vary together, to covary. And for that, I'm just going to define one other thing, which is the mean values. So somewhere around there, that's the mean amount of rioting, mu r, and the mean for the wheat price, it might be somewhere here, so I'll put mu w. Then the covariance, which we can write as v of w r, is defined as, it's 1 over n, the total number of points, into the sum over I, all the points, of wi minus mu w, so that's the individual wheat prices, so take away the mean wheat price, multiplied by the ri minus mu r, which is the individual amounts of rioting at each point, take away the mean amount of rioting. So why is this a good measure of the tendency of these things to vary together? Well, suppose that they do vary together, so that as the wheat price goes up, the amount of rioting goes up, and that will mean that when the wheat price is above its mean, it's higher than usual, the amount of rioting will be higher than usual because they're varying together. So both the wi minus the mean will be positive and ri minus the mean will be positive. Both the wheat price and the amount of rioting will be above their mean. And so this will be a positive number, two positive numbers multiplied together. On the other hand, if the wheat price falls and goes below its mean, then this would be a negative number. But also, if they're varying together, the amount of rioting will also fall and also be below its mean. So we'll have two negative numbers multiplied together, which again is positive. So when we do this sum, we're adding up always positive numbers, and so we'll get a large positive value out of it. But on the other hand, suppose it were the other way round and they weren't varying together, but they were varying opposite to each other. So, we haven't got a chart of it here, but suppose it were the case that when the wheat price went down, the rioting went up, and vice versa. In that case, when the wheat price was high, so this was positive, it's above the mean, the amount of rioting would be low, this would be negative, it would be below the mean. So it'd be a positive number multiplied by a negative number. So this would be a negative value. And then vice versa, if the wheat price goes down, making this negative, so it's because it's below the mean, then the amount of rioting would go up. This would be above the mean, and so we'd again have a negative times a positive, we'd have a negative number. So when we're adding up a whole load of negative numbers, so we'll get a negative covariance, and that clearly makes sense. It's saying that they don't covary together, they covary in opposite directions. So there's a negative covariance. And on the other hand, if they didn't depend on each other at all, they didn't particularly vary, together, then what that would mean is that when say the wheat price was above the mean, so this was positive, some of the time the rioting by chance would be above the mean as well. But other times the rioting would be below the mean. It could be either, because they don't vary together, they don't depend on each other in any way. So sometimes if the wheat price is above the mean, this will be adding, and some other times, just as often, it will be subtracting. So they will tend to cancel out. So we'll get a covariance of 0. And clearly that makes sense. If they're not varying together, then the covariance is 0. So this is a good measure of the tendency of two variables to vary together. And then you can see that our previous definition of the variance, which looked like this, 1 over n, the sum of xi minus mu squared, that could be written as v of x comma x. It's the variance of x with itself, because it would be xi minus mu times xi minus mu, or xi minus mu squared. So the covariance and the variance are, related in that way. Okay, now I've written up here our formula for the covariance, v of x and y. I've just, to make our formulas more general, changed from wheat price and rioting just to more general x and y. Now the problem with this covariance is that the actual value you get out of it is going to depend on the units in which you measure these quantities. If you measure them in smaller units, the numbers will be bigger and you'll get a larger covariance. So to get so you can't really draw many conclusions from the actual size of the covariance. You can, the fact that it's positive, negative, or 0 makes a difference, but the absolute size isn't really telling you very much. So what we want to do is normalize this so that, we can get a feel for what the size of the metric means. And the way to normalize is we divide these differences of the variables from the mean by the standard deviation. So we'll divide that by the standard deviation of x, and the differences in y we'll divide by the standard deviation of y. And now if we change the units, these won't change, because the standard deviation will also change, and by the same factor, and so it will cancel out. And so it's the absolute size of this metric is meaningful, and so this is no longer the covariance. And we call this, in fact, the correlation coefficient. We'll represent by the letter R, correlation coefficient. And why this is a particularly good measure, we can see if we cast our mind back to when we're talking about the normal distribution. This is that Zi, a way of standardizing the variables so that they now vary about 0. The mean is 0, and the standard deviation of this will be 1. That is the variable Zi. And this is also a Zi, but it's not necessarily the same Zi. We'll put that as Zi dash. So this can be written as 1 over n sum of Zi times some other zi dash. And the thing is that if these variables vary together, if they have a large covariance, then, and in fact, if they vary exactly together, then what that will mean is that when x, say, increases by 1 standard deviation, y will also increase by 1 standard deviation. They're varying absolutely together. And in that case, the zi's, which measures the amount of variation in standard deviations, will be the same for both variables. So if these two variables are exactly correlated, exactly depend on each other, they vary exactly in synchrony with each other, then we can say that zi dash is equal to zi. So if fully correlated, this is going to be equal to one over n sum of zi squared. As I've just said, the zi dash will be the same as zi if they're varying exactly together. And so that is equal to z squared bar. 1 over n times the sum of over I of zi squared is the average value of z squared, sorry, the average value of z squared, so that's z squared bar. And that is equal to z squared bar minus z bar squared. And that is because z bar is 0. So 0, if we just subtract 0, of course it doesn't make any difference. So that we could write this as z bar squared minus, sorry, z squared bar minus z bar squared. And that's because we said this variable zi has those properties. It has a mean of 0 and it has a standard deviation as well of 1. Now this z squared bar minus z bar squared is simply the variance of z. And if the standard deviation in z is 1, which is how it is, then the variance is 1 squared, which is also 1. So this is 1. So this correlation coefficient, if they're fully correlated, is 1, which is what makes sense. If they're fully correlated, the correlation coefficient is 1 or 100%. They're 100% correlated. What about if they're anti-correlated? Well, in this case, when x increases by 1 standard deviation, y will do the exact opposite. It will decrease by 1 standard deviation. It's anti-correlated. It does the exact opposite of what x does. So this will be zi times minus zi. So we can take the minus sign out. So we'll have minus 1 over n sum of zi squared. And so that will just be minus this. So the correlation coefficient will be minus 1. That's fully anti-correlated. And then if they're not correlated at all, well, if we go back to this, if they're not correlated at all, the zi dash varies completely independently from the zi. X might increase or decrease, but what y does and what therefore z dash I does, it is not dependent upon that. So if sometimes when zi increases, this may increase, but some other times when that increases, this may decrease. So it will sometimes have a positive effect and sometimes a negative effect. So it will cancel out. and we'll get 0 overall. If they're not at all correlated, we'll get a correlation coefficient of 0. And again, that makes sense. If they're, if they're not correlated, correlation coefficient of 0. And then for intermediate levels of correlation, it's partly correlated. We'll have something between 0 and 1. And we can just write this another way, is this on the top here, sum xi minus mu times yi minus mu y. That is our covariance, which we could write as v of xy. And then we just put the sigma x and sigma y on the bottom. So that's another way to calculate it. If we just calculate the covariance, and then we divide by the 2 standard deviations multiplied together. Okay, we're now going to talk about the idea of fitting a straight line to a set of points on a scatter chart. So here we've got, say, our points for the price of wheat X and the amount of rioting Y, and they're all over this chart, and we want to fit a straight line through the middle of them. And we write that straight line as kind of the ideal straight line, as it's going to be the formula of a straight line, y equals mx plus c, though we write that as y hat, because this is the ideal y. So the points on the line are, for x, the points on the line we would write as yi hat, and the actual points are yi. So if these variables were totally correlated, all the yi would lie on the line, but in general they don't. And what we want to do is minimize the distance between the yi's, the actual values, and the yi hats, where they would be if this, if they lay on this straight line of perfect correlation. So we want to look at this distance, or difference rather, between the ideal values of y on the straight line and the actual values of y, yi hat minus yi. Now, we could just add those up, but we'd have the same problem as with the variance, that some are above and some are below, so they tend to cancel out. So we square it, so it's always positive, and then we add that up, and we want to minimize this expression. We want to find the values of mx plus c that will minimize this sum of differences between the actual values y and the yi hats on the line. Well, yi hat is m xi plus c, so that becomes sum over I of mxi plus c minus yi, and we can then say use techniques to minimize this expression, which we do just by calculus, differentiating this with respect to m and c and finding where the minimum points are. But I won't go through that, because in reality you would never want to do that, and you wouldn't want to use the resulting formulas in a manual way. You would just enter your data into a statistics program like Excel and get it to do these calculations for you. So it's not something we need to carry around in our heads what the formulas for M and C are, but we can just know that by that principle of minimizing this expression, it leads to the values of M and C that correspond to this ideal straight line, the one that goes exactly through the points, or goes through the points with the best fit, so that it's got the minimum distance away of the actual points from the points on the line. And if you're using Excel, scatter plot, you can choose to fit a line, and the formula of the line is an option, for example. So if you're using Excel, which is one I use, that's the simplest way to do it. You take your X and Y's in 2 columns, you do a scatter plot, you then choose from the menu to, on the scatter plot, you can fit a line to it, and then you can look at the properties of the line, and somewhere there's a checkbox you can ask to get the formula for the line, and it will give you the values of M and C. Okay, so I've drawn up again a previous diagram on a slightly smaller scale to give a bit more space on the board. So what we're now going to address an important question, which is that supposing we've found this straight line expressing a relationship between X and Y, or between the price of wheat and the amount of rotting, how much of the variation in this variable is explained by this relationship, or explained by that variable? So if this is again wheat, price of wheat and rioting, how much of the variation in the amount of rioting is explained by the price of wheat? As the price of wheat varies, the amount of rioting varies, and ideally it would follow this straight line. If it was on that straight line, the price of wheat would explain all the variation in the rioting, but in fact the amount of rioting doesn't lie on the straight line, it's somewhere above and below the line typically. So it doesn't explain all the variation. There's a general tendency for the amount of rioting to increase with the price of wheat, but sometimes it goes down, sometimes it goes up a bit more. So we've got 2 sources of variation. The price of wheat is varying, and that's causing the amount of rioting to vary, but the amount of rioting is also varying for other reasons which we're not sure of. It doesn't seem to depend on the price of wheat because it's above and below this line. So how much of the variation in rioting is explained by the price of wheat, or by this proposed relationship between the wheat price and the amount of rioting? So this is our question. How much of the variation in Y is explained by X, or by, we could say, the relationship between X and Y that we're proposing? Well, the total variance in Y, we could say, has 2 components. So Y varies, but for 2 reasons. One is the variance in the wheat price. So that is the variance in Y hat. So as the wheat price varies, the amount of rioting varies. That's given by the line. Wheat price going up and down causes rioting to go up and down. So the points of Y in this direction vary in the Y direction because of this variance in the wheat price. So that's the variance in the ideal values of rioting that would occur if it depended solely on the wheat price. So that's a variance in Y hat. But as we can see, they don't just vary up and down the line, they also vary around the line a bit. So they vary in Y hat, but then they vary around Y hat. So we can say that it's the variance in Y hat plus the variance around Y hat. And that adds up to the total variance. So when we're asking about this, how much of the variation in y is explained by x, the fraction explained is going to be the variance in y hat. That is the variance that is explained by x, because as x varies, y hat varies in this very mechanical way up and down this straight line. That's the wheat price explains that variance in y hat. It's a variance around y hat that the wheat price can't explain. So the fraction explained is this variance in y hat divided by the total variance. So if we can calculate this, we can say what fraction of the variance is explained by this hypothesized relationship, or is explained by x. Well, to find the variance in y, the variance in y hat, that's going to be equal to, just by the standard definition of variance, one over n, the sum of yi minus the mean of or y hat I minus the mean of y hat squared. But the mean of y hat is the same as the mean of y. I'll say in a moment why that is. So we've fitted this straight line through the points so that it minimizes, and there's going to be as many above the line as below it. And so if we imagine moving these lines, points down to the line, if we start with the points where they actually are, they have a certain mean. And as we move one down towards the line, we're also moving others up by the same amount. So for everyone moving down towards the line, others are moving up towards the line by the same distance. And the mean, which is in the middle, is going to stay in the same place. So the mean of y hat is the same as the mean of the original points values yi. And we can also say that the mu y lies on this line because by definition of the mean it has as many points above it as below it, and that's the case for this line. There's as many of the y values above as below, so the mean must also lie on this line. So the mean will obey the formula of the line to be mu y equals mx plus c, or mu x is the mean value of x. So we can substitute in here these expressions. For yi hat we've got mxi plus c, and for mu y we've got that. Okay, so I've replaced yi hat with mxi plus c because y hat obeys that formula, and mu y, we just said, also obeys that formula, so I've subtracted minus mu y minus m mu x minus c. So we can see from here that the c's cancel, and we've got a common factor of m in front of both of these, so we can take that out, but it's squared, so there will be a m squared here, and then we'll have xi minus mu x squared. And we can now also just put this m squared out the front, let's say. M squared times 1 over n sum of xi minus mu x squared. And we should recognise that this is just the formula for the variance in x. This is a standard formula for the variance in x. So it's m squared times sigma x squared. And I should put here the total variance in y. Well, the total variance in y is just the standard deviation in y squared. So this is sigma y squared. So we've got the fraction explained equals that, which is the variance in y hat, divided by the total variance in y, which is just sigma y squared. But now we can relate this m to r and sigma x and sigma y in another way. We can say that m is equal to r times sigma y over sigma x. Now, why do we say that? Well, just try to find a bit of space. Suppose that the y and x were perfectly correlated, so that when x changes by one standard deviation, sigma x, then y will change by one standard deviation in y, sigma y. That would be the case if they were perfectly correlated. And that would mean they would be, all the y and x would always lie on this straight line because they're perfectly correlated. There's no variation around the straight line. So a change of sigma x leads to a change of sigma y. And the slope of this line then is going to be sigma y over sigma x, just by the definition of the slope, the increase in y divided by the increase in x. That is if they're perfectly correlated. So that is if r equals 1. Remember that a correlation coefficient of 1 means that things are perfectly correlated. And then what if r equals -1? Well, I'm running out of space to draw it, but it would be the other way round. When x increased by sigma x, y would decrease this time. So by sigma y, exactly the opposite. So it would now be minus sigma y divided by sigma x. So we'd have m equals minus sigma y over sigma x. And if they were not correlated at all, then as x varied by sigma x, y would neither go up nor down because they're not correlated. It wouldn't change in any particular way. There's no dependence of the change in y on x. So if r equals 0, the line would be straight line, horizontal line. We'd have m equals 0. So just by taking those extreme points, we can see why this works. That if m, the slope, is equal to r sigma y sigma x, this works here. When r is 1, we get sigma y over 6 sigma x, which is what we'd expect. If r is -1, we get minus sigma y over sigma x. And if r is 0, we'd get m equals 0. And then for intermediate values of the correlation, that if, say, there was a small positive correlation, then when sigma x varied, there would be a small tendency for y to increase by a standard deviation, but it would be less than a full standard deviation. And so if r was a fraction, we would again get the slope being less than exactly sigma y over sigma x, but to some extent, as a positive value. So we can sort of justify there, it's not a very rigorous way of doing it, but that we justify there that formula for the slope, which we can then rearrange to say R equals m sigma x over sigma y. And if we square both sides, we get that m squared sigma x squared over sigma y squared, which is the fraction explained. So the fraction of the variation in y that is explained by x is equal to r squared, where r is the correlation coefficient. We saw how to calculate earlier. It's sometimes written as R2. But is therefore a very important factor in telling you how good your straight line is at explaining this relationship. So in this case, it's how much of the variation in the amount of rioting is explained by the price of wheat. Well, it is r squared, where r is the correlation coefficient. So if you calculate the correlation coefficient and you find, well, let's say the correlation coefficient was 0.9, then r squared is 0.9 squared, which is 0.81. So you would say that 0.81 of the variation in the amount of rioting is explained by the price of wheat, or 81%. So that leaves us nearly 20%, which is not explained by the variation in price of wheat. That's this extra variation around the best fit straight line. Now, how to get r squared? This also you can get from Excel, straight line fitting function. It's an option. If you have a scatter plot, you can ask for a fitted line, and one of the options for the fitted line is to show the formula of the line, as I said, and also you can show r squared. And then you can quote that and say, well, I found this variation as this relationship between rioting and the price of wheat, and the price of wheat explains 80% of the variation in the amount of rioting. And people say, well done, you're 80% there to explaining why rioting occurs. Okay, now I'll just say a little bit more about sort of full linear regression, let's call it that. In that we've seen how you can find the formula of the straight line that best fits the points, and you can find your r squared value to give you a metric of how much of the variation you're explaining. But if you look, for example, in the Excel linest function, it gives you more pieces of information, which is what I'll now just briefly discuss. So I said that if you're using Excel, you can do a scatter plot and then ask it to plot the best fit straight line, and it will give you the formula and the r squared. But if you want more information, you can use this linest function. You feed it your two sets of data, the x and the y columns of variables, and as well as the m and c, the slope and the constant, you also get other pieces of information, the standard errors, which in these variables it will give you the standard errors, which is how much they could vary. It's like confidence intervals, really. You can probably best think of it as like that, because you've got a set of variables, but just by chance you could get values for M and C that don't reflect the true underlying relationship, just by the same way as if you throw a dice 60 times, on average you'd expect 10 sixes, but you won't get exactly 10 sixes. So the values M and C that you calculate might not be completely accurate. Now, the more data you have, the better they should be, but how good an estimate they are is given by the standard errors. The larger the standard error, the less good it is. So these show you some degree of confidence in the values you're getting. You also get the standard error of the y values. So this is telling you how good a fit the y values are to the straight line. The larger the standard error, the more scattered they are around the line. Then there is the F statistic. And the degrees of freedom. And you can use those to look up in statistical tables to tell you how reliable your finding of a linear relationship is. So it's a bit like the chi-squared test. It's a bit like the chi-squared statistic that tells you whether the pattern is meaningful or not, how much confidence you can have in whether this is meaningful. Could this straight line just have occurred by chance, or is it something you can say, no, there is definitely a straight line relationship here? So as I say, you can look it up in statistical tables, though in reality there's formulas or functions within Excel that will give you how meaningful this F statistic is, what the probability is at 5% and so on. I'm not going to go through all that. I'm just kind of introducing you to the idea so that you can go and do this for yourself, but you can look up the documentation on LinEst to see what you can do with these if you want to get into that level of detail. Though most people don't report that in their papers. They would just largely just report the finding and the R squared value to give, to say we've explained so much of it. And there's also one other thing, the sum of squares value, which is used in the calculation of R squared, and that's also given to you. So yes, the documentation for that in Excel, gives you an example, sees what it all, so you can see what it all means in practice. So I've kind of talked through what the things are there for you. And I also particularly mention that because we're now going to talk about the idea of multivariable regression, where the amount of rating depends not just on the price of wheat, but on other factors as well. And if you want to investigate that, then you can use this same LinEst function. So let's have a look at that. Okay, so let's consider the situation now where we think that our y depends not just on the price of wheat, but on other variables as well. So this might be the price of wheat. This might be, say, the tax rate. This might be the weather, hot weather we might think, or the temperature, temperature perhaps. Hot weather may make people more likely to riot, you might imagine, and other things as well. So you can have as many as you like, and then a constant at the end. Well, you can use in Excel the LinEst function in exactly the same way as you do for just two variables for this multivariable situation. You'd have one column with your y values, and then you'd have columns for each of your x values, and you feed those in to the linest function, and it will give you the m's and the c, and it will give you the standard errors for the m's and the f statistic and so on, all the other things just as before. And these m's, the slopes mi, is a kind of measure of the importance of the variable in this relationship. So if m is small, then it means that y doesn't really depend very much on that. This can vary quite a lot, but if m is small, it will have little effect on the value of y. Whereas if m is large, then a variation in x will have a large effect on the value of y. So the slopes we calculate, mi, are a measure of importance. But the problem with that is that it depends on the units. So that if one of these is measured in inches and the other is in miles, they may both affect the y in the same way, but the m's will be very different, because one will be in inches, and so will give a much larger number than the other, which is measuring it in miles, let's say.
So to get a better measure of importance, we should multiply the slope by the mean of the corresponding x value.
Okay, I'm lastly going to talk about the idea of nonlinear regression. So here we might have a scatter plot that looks like this. There's x and y and the points like that. And we might say, oh, well, we can draw a best straight line through the points. And then we would derive this linear relationship. And it would be sort of reasonable. But if we look at that, though, we can see that actually this looks not so much like a straight line, but it looks more like the relationship is some kind of curve. So the principle of nonlinear regression is basically the same as with linear regression. We have some curve, target curve, and we try to minimize the distances, to the total sum of distances between the actual points and the points on the straight line. But the trouble is with that, we don't know in advance what curve we're trying to fit it to. But it's not that difficult to just try various options and see which one works best. So we might try a straight line, but we could also try an exponential, for example. And in Excel again, if you've got a scatter plot and you're trying to fit a line to it, it gives you various options. It gives you an exponential as well as linear. That's the main sort of first border call, but you can also try an exponential relationship. You can try a logarithmic, a power law, and a polynomial. So that would be a curve of the form, something like ax cubed plus bx squared plus cx plus d. And you can go, higher than that. You can specify how many powers you want to go up to. You could have fourth powers, fifth powers, whatever. And with a polynomial, you can fit all sorts of weird and wonderful shapes. A polynomial can look like that. So you've got all those options, and what you might do is go through them, try them. You could either look by eye to see which ones are most plausible, but you just try them all and look at what the r squared is, and if one of them gives, you know, a good strong R squared, meaning that it is kind of explaining most of the variation, then you would think, oh, well, that's the one. Now, that's a very crude way to do it, because for one thing, the R squared value doesn't mean quite the same thing in nonlinear regression as it does in linear regression. In linear regression, yes, there's a strong argument that it means the amount of variation that is explained by this variable or by the proposed relationship between the variables. But in nonlinear regression, R squared is related to that, but doesn't exactly mean that. So you can't. It would be very loose to say that it's the percentage. But that said, people do say that, and also what people ought to do is do these F statistics to test the quality of the fit, given the amount of data that you've got. You know, how likely is this to have occurred by chance? Again, people kind of neglect that, you will see, but you know, it is what we ought to do, and what we ought to aim for anyway. Another thing you can do if you're fitting a straight line with a non-linear relationship is if it's a power law that you're fitting, you're trying to fit it something like cx to the minus alpha or something, then, well, I don't need a minus really, just if you cx to the alpha, then you just take the logarithms of your data, c plus alpha log x, and you can then just plot log y against log x and then do a linear regression on it, and you'll get, this will now be, alpha will be the slope m, and log c will be c. That's big C, wasn't it? Again, this is a rather crude way of doing it. The results you get from taking the logarithms and doing a straight line fit will not in general be the same as if you fitted it directly to a power law. So, you know, strictly speaking, this is not what you should do. You should use some software that can do actual non-linear regression to get a better quality result. But, you know, if you haven't got access to that, this is a quick and dirty way to proceed.